Hello, let us start fourth lecture. Now, in this lecture, we will get into the fundamentals behind heat treatment, and whenever we talk about fundamentals, we need to see what fundamentals. Now, as we have seen that four factors: phase, transformation, and then here we see thermodynamics, means whether a particular phase transformation is possible or not. Thermodynamics will decide, and whenever we talk about possibility, we talk about whether there is any driving force for the transformation. So, the driving force. Now, once we see the driving force, that means a particular phase transformation is being driven by some particular parameter force. And then once we see that yes, the possibility is there, or then we need to look at what rate. At what rate. And whenever we talk about rate of phase transformation, we talk about kinetics. So, let us first see the phase transformation part from the point of in the angle towards in order to see the phase transformation, we need to first check thermodynamics. We will talk about that. So, before we start this driving force, let us have some definitions. The definitions are phase. This needs to be defined. The classical definition, we call it as physically distinct. Physically distinct, then chemically homogeneous, part of a system, it has to be part of a system and then we call it a phase. Now, whenever we talk about part of a system, that means one system has to be defined first, and out of that system we have to see what is that part. Now, how do I take that part out? In order to take that part out, we need to see that is there any demarcation between that part from the rest of the system, and that demarcation is nothing but interface. Interface. So, while defining phase, all those keywords are necessary. That means it is a physically distinct, that means its appearance would be different, chemically homogeneous. So, in that particular phase at every point we can have a similar concentration composition, and part of a system means it should be a part of a whole system. And whenever we are talking about a part of a system, we need to see whether that part is covered or separated from the rest of the system with an interface. Now, in order to appreciate this definition, let us take a small example, and we will talk about example like a steel. And in the steel, if we see a kind of a 0.4% carbon steel, and if it is completely annealed structure, means it's furnace cooled, then the structure would look like, so there would be grains, and at the same time there would be perlites, so this is alpha, this is perlite, and the perlite is also a mixture of ferrite plus Fe3C, which is cementite. Now, let us see which one is a phase. Now, here if we see alpha, which is the BCC phase in steel, which is also nothing but interstitial solute solution of carbon in iron, and if we see that this phase is separated from rest of the system, if this one is the system, rest of the system with an interface which is the grain boundary. Now, we need to look at what happens if it is rest of the system, that means it is the part of the system, that part is fulfilled, this part of the system is fulfilled. Now, we need to see whether other things are fulfilled. Now, if we see at different sections, if we see the concentration of carbon in different sections, we would find that the concentration of carbon is almost same, is same at every point within this particular section. So, that means it is chemically homogeneous. Now, the first one, which is the physically distinct, and if we see it under microscope, and as we have discussed in previous classes, lectures, that whenever we try to see microstructure of a steel under microscope, we need to electrochemically etch it by a nitrile solution, and then if we see under microscope, we will see this kind of structure, and these phase would look bright. So, that means, and rest of these phase would look grayish. So, that means these phase has a distinct physical appearance, that means it looks bright. So, that means it is also physically distinct. Okay. So, that means we can say that this is a phase. Now, this part is also alpha, this is also a phase, this is also a phase, this is also a phase, this is also a phase. But now, what happens in the perlite? In the perlite, if we see that this particular thing, if we see under microscope, we will see that these particular stuff would look like a white strip, and this is nothing but Fe3C, which is cementite. And these part which would look, so this is not white, rather I am wrong, this will not look like white, this is a strip which would look like a dark strip, and these will look white. It is just wrong, this is the dark part, I am sorry, this will be the dark part, and then these section would look bright. Now, here these are nothing but alpha, again this is alpha, but it would have a different composition than this. Okay, we will come to that why this would have different composition than this. Now, once we have this, now you have a dark phase which is cementite, we have a bright phase which is alpha, and at the same time if we blow it up at this particular zone, if we blow it up, we will see that this is alpha, this is Fe3C, and this is Fe, this is alpha again. So, that means this is an interface. So, that looks like again this particular zone is separated from the rest of the system with an interface. And also if we see at different points within this, if we see the composition, we will see that the composition will be same everywhere. The carbon percentage would be 6.67%, and that means this is chemically homogeneous, and also under microscope it looks like a dark phase. That means it is physically also distinct. So, this is a phase. Now, adjacent to that, that alpha is also surrounded by a boundary, and it is separated from rest of the system, and every point in this would have same composition. So, that means it is also chemically homogeneous, physically distinct part of the system, separated by a boundary from rest of the system. So, that means the perlite is not a phase, rather it is a mixture of two phase. So, that means it is a phase mixture. So, never make any mistake like that, that perlite is a phase. The perlite is not a phase, because it is not a distinct part, rather it has two distinct parts, and those two things are ferrite and cementite, and this ferrite is called alpha and cementite is Fe3C. So, it is a phase mixture. So, now we understand what is phase. Now, whenever we talk about phase, it can have different distinct nature. Like let us say a pure component system, let us say a pure metal, let us say aluminum, and if we take it to beyond 660 degrees Celsius, then it would melt. Okay? So, it would have, though the composition would be same, that means the pure metal, but at melting point, beyond melting point it would be liquid, below melting point it would be solid. So, that means it has two distinct nature, though the composition is same, but physically they are two distinct phases. Okay? So, that means it is a liquid phase, it is a solid phase. So, composition can be same, but at the same time we need to see whether they are physically separated or not. So, we see that if we have a pure metal, aluminum, a liquid as well as solid, then we say that it is a phase mixture again, and where we have two phases, one is liquid, one other is solid. Similar like water, ice water mixture. So, the ice water mixture, ice is a phase which is a solid phase, and liquid water is another phase which is a liquid phase. Now, when we talk about phase transformation, then we always see that if we take ice out from a refrigerator, we see that at normal temperature, room temperature, in Indian context, it melts. It melts means solid transforms to liquid, or other way around, if we take the liquid water inside refrigerator, after some time it solidifies, it becomes a solid ice. So, that means there is also a transformation is taking place, that means solid to liquid as well as liquid to solid. You can also have other transformation, a solid state transformation. For example, this perlite transformation happen, perlite which is alpha plus Fe3C, that transformation happens from gamma which is FCC iron. So, from there one BCC phase alpha and one Fe3C phase appears. So, both the phases are solid, this is also a solid phase. So, that means it is a solid state transformation. So, we can have solid state transformation, both the phases could be solid, the transforming product is a solid, and from where it transforms, that is also a solid. But we can also have a liquid solid transformation, the transformation product could be solid and then it melts, then it forms liquid, or the other way around, when liquid solidifies, we call it a solidification. That time transforming product is solid, but that from where it transforms, that is a liquid. Now, in order to see phase transformation, we also need to specify whether it's solid liquid transformation or solid solid transformation or gaseous solid transformation or gas liquid transformation, anything can be possible. Now, whenever we talk about that, then complication arises whether it's a pure component, whether it's a mixture, whether it's a solution, all those situations would arise. Now, in order to simplify those complications, we can go one step ahead, one step by step. For example, initially we will consider one component system. One component system, and then finally we will go to binary system, and later on we would see that if we have more than two, if there are two components, we call it a binary. If we have more than two components, we call it ternary, if it is three component. Then as we increase the number of components, things becomes complicated. So, in order to address those complicated system, we need to go and understand what is the thing in what is there in a simple system, which is one component system. Whenever we talk about one component system, in most of our engineering applications, we talk about solid liquid transformation. Okay? Classic example is casting. Okay? The casting, what we do? We melt metal, we form a mold, and inside that mold we pour the liquid metal, and the liquid metal takes the shape of that mold, and we get desired shape, and little bit of machining, a little bit of processing, okay, we get to have a final product. Examples? For example, engine blocks, engine heads, those are all cast products, because those are complicated, and these complicated products can be obtained by casting. Now, so first consideration would be one component system, and in that one component system, we look at liquid solid transformation. And whenever we talk about liquid solid transformation, we take both. That means liquid transforms to solid or solid transforms to liquid, when that would take place. Okay? And why that should take place. In order to answer that, we need to get to the fundamental aspects, which is driving force. And whenever we talk about driving force, we talk about thermodynamics. Okay? Now, after this, let us get into some of those basic thermodynamic functions. Okay? We will not talk about thermodynamics as it is taught in thermodynamics course. We will just take those things which will be useful for our purpose in heat treatment. While understanding the concepts of heat treatment, we will be talking about some functions. Okay? So, let us see those functions. Driving force. Whenever we talk about driving force, and in normal solid liquid condition, that means in the solid and liquid, we can call it, we can term it as incompressible solids or incompressible material. Okay? So, that case, our normal practice, we maintain pressure constant at 1 atmosphere pressure. Okay? And that time, the driving force is decided by term G, which is Gibbs free energy. This is a very, very important function which would decide whether a transformation would be possible or not. Now, whenever we talk about Gibbs free energy, and that time why it is called free energy? Now, we could have called it Gibbs energy, would have been fine, but we also incorporate one word called free. This free term comes because this particular free energy, this particular energy term would be available to do some useful work. That is why it is called free energy. In a system, we have lot of energy, which is decided by the total heat content of the system, which is called enthalpy. There is one more term called enthalpy. Okay. But this total heat content of the system would not be available to do the work. Rather, the part of that particular work will be available to do the work, and that is free energy. And in order to decide how much will we get out of the system for doing work, then another term we have to consider, which is called entropy. So, these three parameters all are energy terms. These three functions would be required in order to understand whether a phase can transform to other phase. And in order to decide that, we need to see what, we need to find out what would be the values of those particular functions. Absolute value of these particular functions cannot be obtained. And at the same time, we need to have some measurable quantity, which we can measure with the help of some experimental facilities. Okay? And then that measurable quantity we can use in order to find those functions. And whenever we try to find those functions, we try to find the change in values. We can decide what could be the, we can measure what could be the change in values. So, that means we can measure change in enthalpy, change in entropy, and change in Gibbs free energy. Okay? And in order to do that, the measurable quantity what we have is basically Cp, which is the heat capacity. Heat capacity. And these heat capacity, because why we are calling it Cp, because we have kept the pressure constant, because this is a condensed system. So, we will be fixing the pressure, and that is what it is called Cp. At constant pressure, what is the change in heat capacity? So, heat capacity definition wise, it is nothing but dH dt P, which is the change in enthalpy or the heat amount of it with temperature at constant pressure. So, that means from this relation we can say that this we can find out from Cp dt, this we can find out Cp T dt. Okay. So, whenever we take this, so that times it becomes this, it becomes this. So, that means whenever we integrate, it is to be finite quantity. Now, what is the relation? Once we have these two, we can find out del G from this formula. So, that means we calculate this one individually, this one is to be calculated individually, and then finally, at the temperature where we would like to find out the change in Gibbs free energy, we just use this formula. Okay. So, now if we try to see graphical representation of all those things, we can also do it. Okay. So, in order to do that, let us plot the change in Cp as a function of temperature at constant pressure and change in H and enthalpy and as well as entropy. So, this is my temperature. Now, if we try to see the variation of Cp, the Cp varies in this fashion. This is Cp as a function of temperature. and this is 0 Kelvin. This is in Kelvin scale. Now, whenever we have this Cp, we need to specify whether it is a 1 component or 2 component, what system it is. Now, as we have mentioned before, that initially we are considering 1 component system. One component system, let us say pure metal. Okay. So, the pure metal, that means we are considering that it is 100% pure. Though in the last lecture, last 2 lectures, I think in the first lecture or second lecture we have discussed that getting 100% pure metal is absolutely impossible, and the reason is the entropy term. Well, if we come across that, we will discuss, otherwise we will just keep continuing with our understanding of this free energy and other things in order to get to the heat treatment concepts. Now, if we have Cp variation like this, then enthalpy varies like this. This is H, this is temperature again, and entropy varies like this. So, this is S, this is H. Now, this H is crossing the temperature line, and when it crosses, it takes a value of 0. So, the enthalpy value becomes 0. Now, this 0 can be anywhere, is not it? At any temperature it can assume a 0 value. But in thermodynamics, in order to find some value, we have to set up a reference state. For example, in order to measure a height of a building, we need to see that from the datum, that means from the first floor, what is the, rather from the floor of the earth, what is the height of that particular building. But let us say instead of, and that time it becomes let us say 100 meter, and let us say I dig up and then measure the height from the basement, I get 110 meter. So, now who is right? I am also right, that the other person is also right. So, that means in order to make both the right, we need to specify what is the reference. And the reference state is in the stablest condition of a pure substance at 1 atmosphere pressure and 298 Kelvin, H takes 0 value. That means the most stable substance in pure metal is basically solid. So, the H solid would be 0 when temperature is 298 Kelvin and pressure is 1 atmosphere pressure. So, that means if we consider this is the solid line, this is the solid enthalpy change, this temperature would be 298 Kelvin, okay, and that time pressure is 1 atmosphere pressure, and this is nothing but the standard state. So, this is my reference, this is the reference data, the datum value, and from that we measure the value of enthalpy of other substance or the same substance at different temperature. So, let us stop here. Okay. We would continue on the same topic in our next class. Thank you very much for listening.